Good afternoon, everybody. We are going to start the second session on fifth day of this STTP. Before this, I would like to introduce our today's expert, Dr. Avinash Agrawal, sir, who is going to present his topic on fuel for sustainable future. So, Dr. Avinash Agrawal, sir, is currently working as a professor in Department of Mechanical Engineering at Indian Institute of Technology, Kanpur. He has earned his postdoctoral from Wisconsin Madison's USA, University of Wisconsin, USA, in 2001. His PhD from Center for Energy Studies, Indian Institute of Technology, Delhi, in 1999. His MTech from 1996 from Center for Energy Studies, Indian Institute of Technology, Delhi, and BTech in 1994 from Malavia Regional Engineering College, Jaipur, University of Rajasthan. He has been awarded the award of Shanti Swarup Bhatnagar Prize for Science and Technology in Engineering Science 2016 by CSIR, Government of India. He has also been awarded the Clarivative Analytics India Research Excellence Citation Award 2017 by Clarivat Analytics, and Rajiv Goyal Prize in Physical Science in 2015 from Kurukshetra University. The Sir holds the fellowship of Indian National Academy of Engineering and International Society for Energy, Environment and Sustainability. He is also a fellow of American Society of Mechanical Engineers, that is ISME, and fellow of SAE International, that is Society of Automotive Engineers International, USA. The Sir has served as an visiting, I think, research fellow in Engine Research Center, University of Wisconsin, Madison, USA. He has also served as visiting professor at University of Loughborough, UK, and visiting professor at Technical University of Vienna, Austria. Sir has also served as assistant professor at IIT Kanpur and associate professor at IIT Kanpur. Then he has again visited worked as a visiting professor at Tashwan University of Technology, Pretoria, South Africa, and Hanyang University, Seoul, South Korea, and Technical University of Vienna, Austria, and Hanyang University, Seoul, South Korea. And also he has served as a visiting professor at KAIST Daejeon, South Korea, and right now he has been serving the IIT Kanpur since March 2012. The Sir, in his credit, has published 207 papers in referred journals and 90 papers in international conferences. The Sir has written 24 books and has edited 42 chapters in different type of books. He has also published 7 policy-based publications, and under his able guidance, already 13 students have completed his PhDs, and 3 students are doing the PhDs right now, and 44 students have completed masters under his guidance. Sir holds the 3 international patents and completed 25 research projects, and he has also published other numerous publications in technical and other related fields, and he has been teaching the different subjects of mechanical domain in vast, you can say that a vast area of educations. So with this very big profile, I'm not able to read out all those things that he holds in his credit. So without wasting much time, I would like to hand over the session to Dr. Avinash Agrawal, sir. And today's topic he is going to present is on fuel for sustainable future. So please, Avinash Agrawal, sir.
Thank you, Dr. Badrakia, for introducing me. Lavish introduction. Thank you.
Sir, may I request, your voice is very low. So can you please increase your voice?
I don't know how to do that. Is it better now?
Yes, somewhat better, but if you can wear, I think,
You can
headphone or
increase the
microphone.
volume.
No, I think, sir,
Volume because
you should wear, I think, headphone or microphone.
no, it's my microphone is in the
Inbuilt. It is inbuilt.
inbuilt in the
Okay.
camera.
Okay, no issue,
I
sir.
can
Okay.
be a little bit closer and try to speak louder.
Okay. Okay, sure,
You
sir.
can also try to increase your own volume at your place.
Sure, sir. Okay. Okay.
All right. So first of all, thank you very much for inviting me. Anurag Emmanuel was chasing me for this, so thank you for inviting me here. Dr. Rakesh Patel, thank you very much for inviting me. I see my old friend Ronak Shah also here. He has invited me several times to give talks in AICT sponsored programs. So, can you tell me how much time do I have to speak and what kind
So,
of
so
interaction?
you have 2 hours up to 2 p.m.
Okay, so maybe I will take about 45 minutes to 1 hour. 2 p.m. will be a little long.
Okay,
Uh,
Okay.
okay, no problems.
45 minutes to 1 hour to discuss the various dimensions. And then, audience can ask any number of questions and, up to whatever time it goes. I hope that is fine.
Okay, sir.
Yes,
Okay.
yes, sir. Yes.
All right, I'm sharing now my screen. Can you see my screen?
Yes, yes, sir.
Yes, sir.
Okay. So I'll be talking to you about fuel for sustainable future, and I'll be talking about a lot of fuels which will be part of sustainable future. And in particular, I'll give a little bit more stress on green and environment friendly methanol economy. This is a concept which is being advocated by Niti Aayog of late in last 5 6 years. So I'll discuss about that as well. So today, if you look at the world, there are three major challenges that we face in the world today. And these three major challenges are actually linked to each other. First challenge that the world faces today is depletion of natural resources. So when you say natural resources, you are basically talking about uh, fuels of different kinds, which are from fossil origin and which are converted to energy to meet different kind of requirements, be it coal, be it natural gas, be it petroleum products and all that. The second challenge is also because of the first challenge, and that is what we are doing is that we are taking these fossil fuels from below the surface of the earth. We are using them in different applications such as power plants, such as transport sector, such as agriculture sector, and putting the products of combustion into the atmosphere. Products of combustion could include carbon dioxide, carbon monoxide, oxides of nitrogen, and so on. So this has actually changed the composition of the atmosphere quite steadily and quite fast. And this has led to global warming. Just to put things in perspective, in last 150, 170, we have increased the CO2 in the atmosphere by 50%. Before the industrial revolution in 1850, the CO2 concentration in the atmosphere was 280 ppm. As we talk today in 2022, the CO2 concentration is 410 ppm, good 160 ppm more than what it was only 150 years ago, 170 years ago. And this is not fixed. This is increasing at a rate of 2 ppm per year in the atmosphere. And that has given rise to a lot of issues that we see every day. We see global warming, we see the temperature going up, we see actually more precipitation, we see more frequency, higher frequency of cyclones, higher frequency of natural calamities, floods, and all that. So it is all our own making. So this is one serious issue that has happened because of the global warming. And then on top of it, we have gone for civilization where there is a lot of stress on making cities or living in the cities. So we have these cities which have become gas chambers because we use a lot of transport vehicles, a lot of other means where we burn fossil fuels. And these cities, unfortunately, have become gas chambers. So there is an issue of urban air quality in the cities, which is causing a lot of health cost to the population. So these three problems are interrelated, and these three problems are what the humanity faces today, and that needs to be really addressed. And for addressing this, now you must have heard about COP21, COP26, Paris Agreement, Kyoto Protocol. So all the countries are making combined efforts to control the GHG emissions into the environment, to move away from fossil fuels, to improve the urban air quality and so on. So all these problems are interrelated. So this is just one submission on a very, very broad scale of what we are doing, why we are doing, and how we are doing. Now, whenever we talk about fossil fuels and oil, see, we have made these artificial boundaries of India, Pakistan, Canada, France. So humanity is one. There is only one humanity all over the world. And every citizen of the world has equal rights on the resources of the world. Now we have divided this whole world into countries. So let us look at the countries, how much resources we are consuming. So in this context, as I'm talking about fuels, so I'm just going to look at the oil, petroleum. So if you look at the oil, 26% of the global oil is consumed by United States. 7% is consumed by Japan, very small country. China, which is much bigger than us, it consumes about 6%. Germany, very small country, consumes about 3.6%. And here is India, consuming only 2.6% of the global oil. Now, I would like you to give this attention to this number 2.6% versus 24%, 26%. So see, India is at least 4 to 5 times more populous than United States. And United States consumes 10 times more oil. So that means they also put 10 times more CO2 into the atmosphere. So on a per capita basis, we are already consuming 1/50th, 1/40th to 1/50th of the oil uh, that an average American consumes. So whenever we talk about any climate justice, any energy justice, we have to keep this in mind that India is already on very, very low scale. So whenever we go to any negotiation, we have to make sure that although as a country we consume 2.6%, but on a per capita basis, it is only 2 to 2.5% of what an average American is consuming. So whenever we talk of a climate change or climate, energy, we should also talk about climate justice and energy justice. And I think we are on the receiving end of this. India, as India grows, as India develops, as India transitions from a developing economy to a developed economy, this number is bound to go up 2.6%, maybe 5%, 6%. And we don't need to feel guilty about it because we are very efficient in terms of per capita consumption. We are still a fraction of the developed world, and developed world is developed because they consume more amount of energy. India will develop because we will consume more amount of energy as well, but in a more responsible manner. We will consume energy which will be mostly from CO2 free sources. That means we will not overburden the environment with CO2 emissions. Okay. Please feel free to ask any question. If there is any question on any slide, please feel free to interrupt and ask questions. I'll be very happy to answer those questions. Now, if you look at the time scale of 50 years, starting from 1950 to 2050, this scale shows the global energy consumption, and this just shows how we have transformed our energy requirement and where it is going to come from. So between 1950 to 2000, in 1950, the whole world consumed very small amount of energy because, of course, there was not much penetration of electricity, very few vehicles were there. So from 1950 to 2000, it grew at an average rate of 4% per year. And after 2000, for the next 50 years, it will grow at roughly about 3% per year. Okay. So far until 2025, the energy requirement will be mostly met by oil. Mostly it will be oil. But then we all know that oil resources are limited. Oil wells have finite period. And at some point in time, in near future, the oil will peak. So that means the oil supply will stagnate. And then after that, the oil will start running out. So oil supply will start dwindling. But our demand will keep rising. So the question that every government, every policy planner will face is how to bridge this gap. Every time will increase, this gap will keep on increasing. So the answer to that question is that we will then shift to natural gas. So natural gas nowadays, the natural gas is being used in a big way in different applications. For example, it is being used as compressed natural gas. It is being used as liquefied natural gas, and so on. So we will keep using it, and we for next 10, 15 years, natural gas will be able to support our economic activities. But then natural gas also being from fossil origin will peak at some point in time, and its supply will also start dwindling. And then we will require unconventional sources of energy. So that means by 2035, we will have a lot of unconventional energy sources which have to be made commercially viable, and also they have to propagate in a large manner so that the civilization can be supported and we don't return to medieval periods where there is no energy, no light, no vehicle transportation, and we are traveling from one to another place on horses or on bullock carts. If we don't want that kind of future, we have another 15 years to make sure that unconventional energy sources becomes economically viable to bridge this gap and okay. And this is the sources of this information is given in the bottom. Now, this sustainable transport, if you look at the sustainable transport, it's a very noisy space and it's a very complicated one. Let us try to understand what is transport system and what is sustainable transport. So see, when we talk about the transport system, we are basically talking about four modes of transport. We are talking about road transport, we are talking about air transport, we are talking about marine transport, and we are talking about rail transport. These are the four modes of transportation that we are talking about. We are still not talking about Elon Musk's all these space transport vehicles right now. Okay. So now when we talk about transport systems, so transport systems have environmental impact because all of them right now, they work on fossil fuels. So they will have environmental impact. Transport system contributes to about 16 to 23% of the global GHG emissions. And as the transport is increasing, it is becoming more and more involved in our economies. This emissions from 16 to 23% is going to go up.
Excuse me, sir. Avinash, sir.
Yes.
Sir, your slide is not changed. It's fixed on first slide.
I think this is the problem with the. Let me share it one more time. It is the problem with this Google Meet is not such a friendly platform. What slide do you see now?
Sustainable transport system, noisy space. Slide number 5, sir.
Did it change now?
No, sir.
There is a problem with the. Can we switch to another platform? Can we switch to Zoom?
Mm,
No, sir, since all the participants are in Google Meet only. So we have to stick to this platform only, sir.
Now I can share the link immediately with all the participants. And these days everybody has Zoom. Because if my slides are not changing, how am I going to deliver the talk? This is a problem with the platform. I can try one more time.
sir, you first of all, you open your presentation in another tab. Then you.
I have done that. Does it change now?
Yes,
Yes,
sir.
sir.
Now it is
Yes,
perfectly all right.
yes,
Perfectly
yes,
all right.
yes.
Okay, so should I explain right from beginning? This I have explained. This I have explained.
No, from fourth slide, fourth or fifth slide.
So I was here.
Yes.
All right. So, so as I said, this transport system has a direct impact on the emissions. So it has a environmental impact dimension. It has a societal impact because all this transport system, large number of people are employed in this. So it is a social dimension in terms of job creation, in terms of poverty reduction, in terms of impact on the energy security, and so on. It has an economic dimension because the entire economic activities of the world actually now depend on transportation. Goods have to move from one place to another place. People have to move from one place to another place. Then there is a job creation in the transport sector and allied sectors, job creation in manufacturing of all these transport machines and so on. And there is a profitability of the stakeholders along the value chain. So the transport sector, in a way, is a very noisy space, having a direct impact on the environment, direct impact on the economy, and direct impact on the society. But if we look at it, there are many players. There are many things that affect the transport sector. There is, with increase in mobility, there is a huge demand for mobility. Everybody wants a personalized vehicle. In India, young graduates of our engineering colleges, they graduate within 1 or 2 years. They want to have their own car. Our students want to have their own personalized two-wheelers and so on. Then, new technologies are coming in the transportation space. For example, there is a explosion of activities in the space of electrical vehicles, hybrid vehicles. Different types of biofuels are being tried to power the transportation system and to displace conventional fuels. There are new types of players that have come into the market. Nobody have thought that Google, Apple, all these people will think of making cars, and now they're trying to make cars. You have Tesla, which was not heard of, and the conventional companies such as GM, Ford, Chrysler, all these will get sidelined, Tata, Mahindra. Now you will be surprised that the Tesla, the entire valuation of the Tesla is more than all the American companies put together. GM, Ford, Chrysler, their valuation is less, and Tesla's valuation is much more. So new companies, IT companies, mobile companies, social media companies, all these companies are coming and playing a big role in the transport sector. Then government policy, is of creating jobs, of energy and transportation, agriculture. This also plays a very important role in the transport sector. Similarly, customer behavior plays a very important role in determining a lot of things in transport sector. For example, the demand for efficiency, the demand for integration with the network. Nowadays, you have connected cars, people want to be connected with the network all the time. And then the sustainability of the transport sector is also very important. Customer demand, actually. And then there are many exogenic factors, for example, economic shocks and resource scarcity and so in a way, this transport sector and transport space is a very noisy space, and finding a sustainability in the transport sector is the key for future, keeping all these factors in mind. So it's a very mind-boggling complex system. Whenever we talk about the sustainability of transport sector, essentially we are talking about sustainable fuels, the fuel which do not affect the environment significantly, they can be produced easily, and they are economically viable. That's what sustainability really means in the transport sector. So whenever we talk about new fuel adaptation in the transport sector, the fuel has to be evaluated on 7 very important parameters. The first parameter is climate impact. What impact the new fuel is going to have on the climate. Is it going to produce more carbon dioxide or more carbon monoxide and so on? And a sustainable fuel has to have minimal impact on the environment. The second factor is energy efficiency. That means the fuel efficiency, vehicle efficiency has to be better than the conventional ones. And then land use efficiency. For producing some of the fuels, you require land. And land is a very important resource which is not infinite. So you have to look at what kind of land resource efficiency you have, how much land is required for producing how much quantity of fuel. The fuel has a potential, large scale potential or not. Can it really be scaled up to power the entire country or the entire world? Or it is just a small scale solution? This also plays a very important role. And then the fifth factor is vehicle adaptation. That means what is the kind of change that is required in the vehicle? For example, I'll give you an example. If you have an IC engine car and somebody says convert it to electrical vehicle, you have to actually take the engine out, put a battery and motor and all that, and that will require a huge cost of converting your vehicle or vehicle adaptation of the electrical vehicle technology. So it does not make sense. You rather sell your IC engine vehicle and buy an electric vehicle. That will be more sensible thing to do. So the extent of adaptation in the vehicle that is required also is a very important thing. For example, I'll give you another example, which is not as radical as EV. For example, if you have a CNG vehicle or a gasoline vehicle, and then you want to convert to CNG, the adaptation required is not very high. Only 30,000, 40,000 rupees will be required to retrofit a SI engine vehicle with gasoline to SI engine vehicle using CNG. Sixth factor, which is also very important, is fuel cost. How much the cost of the energy is. So per megajoule, how much the fuel is going to cost, and fuel infrastructure, whether to produce that fuel, you have adequate infrastructure, possibility of producing that particular fuel on a large scale. So these seven factors are very, very important. And then, looking at the GHG emissions, one thing is for sure that CO2 free fuels are the future. If you want a sustainable fuel, it has to be free from carbon dioxide. That means it should not put additional CO2 burden into the environment. You put CO2, in the next cycle, that CO2 should be fixed back onto the earth. So if we look at some of the sustainable fuels or some of the fuels which are getting popular with time, which are touted as sustainable fuels, it's a busy space. This is having a lot of candidates, for example, methanol, ethanol, hydrogen, biogas, dimethyl ether, biodiesel, synthetic diesel, etc., and combination of these. So these are some of the fuels that are being looked at, and I think you will find that there are hundreds and thousands of papers exploring the use of these fuels for different applications. But one thing is for sure, that going forward, the fuels of future are going to be liquid fuels, and they will still be made from crude oils in the refineries. The question that is asked is that why do you think that the fuels of future are going to be liquid fuels? And the answer is simple, that the energy density of these fuels that we use is unparalleled. No other material present on the earth has such high energy density other than the nuclear fuels. For example, gasoline is about 32 megajoule per liter, or about 43, 44 megajoule per kilogram. Similarly, diesel is about 36 megajoule per liter. That's about 44, 45 megajoule per kilogram. Such high energy density in 1 liter is impossible from any other fuel, any other substance other than nuclear fuels. So this high energy density makes sure that you put enough energy on board without having too much weight or too much volume to carry, and you can travel reasonable amount of distances on the surface. Liquid fuels are very easy to transport, very easy to store. Handling is also, we have now over 100 years of experience, and there is an extensive distribution network. So I don't see any deviation in this. Then in future, fuels are not going to be liquid fuels because of the advantages that the liquid fuels offer. Now, this is one very important, projection which is for 50 years horizon between 2000 to 2050. And on the y-axis, you see billions of vehicles. So, here different countries are shown. So if you look at 2000 beginning, you will see that more than 70% of the vehicles in the world were in Europe and North America. Rest of the world had less than 30% of the total number of vehicles. Now in America, in 50 years, there is going to be very slow growth. In Europe also, it's going to be very slow growth in terms of number of vehicles. Why? Because in America, already you have about 920 vehicles per 1,000 people. Europe has about 700 cars per 1,000 people. So they are already close to one. You can't get more than one per person on an average. But that's not the case in India. In India, right now, you see, right now we are in 2020, and this light green is our number. And we have mobility, we have cars, about 23 cars per 1,000 people. Now compare that with 700 and 900. So there is a lot to grow there. So if you look at it, the growth in the number of vehicles is going to take place in these three triangles that you see here, which actually represents China, Asia, and India. Okay, so the growth is in Asia, and that is why in next 50 years, Asia is projected to be the engine of growth in the world. Asia will propel the global economy for next 50 years or so, because that's where the growth is. And even with these numbers, by 2050, we will maybe at best cross 100 per 1,000. 100 cars per 1,000 people. It will still not be very high. Still, the cars will be 4 times, 5 times from what we have today. And still, even for those managing the roads, managing the parking, managing the energy security is going to be a huge challenge for us, even with those numbers. So you can actually, this picture actually gives a good idea, a good snapshot of what is in store as far as the economic activities, as far as the development activities, as far as the growth in the world is concerned, where the playground is going to be. So the playground for growth is going to be in Asia, and Europe and America has more or less stagnated. They will maintain their standards though. They will not become poorer, they will not become richer, but the growth will be in India. Now to power all these increasing number of vehicles, you will need, India has to look at different fuels. The fuel, right now we are importing 90% of the fuel. We can't keep on importing same. I mean, today we are importing 90%. When our fuel consumption becomes 10 times more, we still import 99%. What is the fun? So we have to look at some indigenous fuels. So the fuels that are being looked in the country and elsewhere include basically biodiesel, synthetic diesel, dimethyl ether, methanol, ethanol, biogas plus biodiesel, hydrogen plus biogas, electric vehicles, hydrotreated vegetable oil, and so on. And they are evaluated on the 7 factors that I just discussed. And against each, you will see a rectangle. In the rectangle, if the rectangle is large, is dark in color, that means it is good, it is positive, and if it is light, that means it is less preferable. For example, electric vehicle have very low climatic impact, very high energy efficiency, very good land use efficiency, very good fuel potential. But the vehicle adjustment required is complete, total. You have to change. Fuel cost may be reasonably good, but the fuel infrastructure just does not exist. So that way, we will evaluate each fuels and you can look at the color. So if you look at this entire matrix, 2 fuels that stand out very distinctly, one is the dimethyl ether and the other one is methanol. Ethanol also has issues, but methanol and DME, they stand out, and they basically are one of the important future fuels as far as India is concerned. I'll talk more about it later in my talk. So these 2 fuels are also touted as electrofuels or e-fuels, and they are also called fossil sunshine. This is One slide that I have taken from China, it is not an Indian plan, but it's a Chinese plan. It was shown by some researchers from China in a conference in Stanford. And I have copied it here just to show what Chinese are trying to do. So, today what they are trying to do is that they are producing the methanol, today using fossil fuels. They are using basically coal, high ash coal, which they have in plenty. They are using petroleum, residues of the petroleum, and natural gas. So what they are doing is they are converting into methanol. Basically, they are converting into syngas, so producing CO plus H2. Then they are correcting the stoichiometry and they are producing methanol. And today they are using the hybrid systems. And the first deployment of this fossilized sunshine will be in 2020. Slowly with time, what they will do is they will displace this coal and petroleum. They will increase their reliance on the natural gas and also on biomass. So then, natural gas and biomass will be converted to syngas, and from that they will, via a hybrid system, they will develop cleaner methanol. And this technology, the prototype will be deployed first time in 2040, and the mass deployment of the same will take place in 2050. Okay. And then what they will do is they will simultaneously keep on doing research, and they will use electricity from CO2 free primary sources such as solar energy and wind energy. They will extract carbon dioxide from thin air in the atmosphere. I told you 410 ppm is there in the atmosphere. So they will separate the CO2 from the atmosphere. They will split the water using the electricity from CO2 free sources, generate hydrogen. Then they will combine this hydrogen with the atmospheric CO2, which they have captured from the thin air. And then they will convert into methanol, which will be completely green. And 2070, they want to mass deploy this system. Now you imagine electricity that is being used is from sun, CO2 is from the atmosphere, you produce methanol, you use it for your transport sector, you put it back in the atmosphere, it is absorbed back again. So this will be a net CO2 free, basically net CO2 free deployment. So they will then be able to meet all their obligations for CO2 reduction in the transport sector. So this is a very, very good plan of deploying the methanol economy and also making it less and less dependent on the fossil and more dependent on the cleaner fuels, and shift their economy from fossil based economy to methanol based economy. Do you have any questions so far?
No, sir.
All right, so let us now look at the properties of the conventional fuels and alcohols. This is just a table. You can find these properties in any book. And I have just compared the important properties of methanol, important properties such as octane number, density, latent heat of vaporization, heating value, flammability limits, autoignition temperature, and stoichiometric air fuel ratio for methanol, ethanol, gasoline, and diesel. Now, please note here that ethanol and methanol have octane number of 106 and 107 compared to 92 to 98 for gasoline. Okay. So these two fuels can be very easily used as a spark ignition engine fuel. If you look at the latent heat of vaporization, this is much higher, 3 to 4 times higher than gasoline. What it really means is that when you inject the ethanol and methanol in the intake port of a SI engine, this will cool the charge. And when we know that when the charge is cooler, it shrinks, and then therefore, it shrinks and then the boosting happens. So you will be able to induct more charge, more fuel air mixture in the engine. So the power output will actually increase from the SI engine when you power them with methanol and ethanol. Similarly, heating value, if you look at, methanol has about 50% oxygen, ethanol has about 65%, 35% oxygen. So it has lower calorific value compared to gasoline. So you will require larger fuel quantity, fuel mass for traveling the same distance. Similarly, auto ignition temperature, if you look at, The auto ignition temperature for the gasoline is 246 to 280, and here it is 464 and 423. Compare that with diesel, which is 210. So what it means is that you cannot really burn these methanol and ethanol in a diesel engine directly. So these are mostly spark ignition engine fuel. If you want to use it in diesel engine, you have to employ some other techniques of ignition. So this table, actually, if you study this well, you can actually figure out different strategies that you will be requiring to actually power your engines. Okay. So if you look at the comparison of biomass, alcohols, hydrogen, and battery on different parameters such as energy density, storage cost, transport cost, and environmental impact, alcohols turn out to be quite positive and battery turns out to be quite bad. And now this is very contrary to what you have heard, that battery is all good, but energy density wise, battery is very poor, storage cost is very poor, transport cost is very poor, and also the environmental impact of the battery is poor as well. Now this methanol and DME are close cousins of each other. You have methanol is CH3OH. If you take two methanol, remove water from in between, you are left with CH3OCH3. So that's the dimethyl ether. Methanol has high octane number of 100 plus. It has clean burning fuel and it is about 15.8 megajoule per liter energy density. It can be used as M85. Now, dimethyl ether is CH3OCH3. You have removed water from here. It's a very high C10 number fuel. Its C10 number is close to 75. Diesel has a 65 or so. And diesel has a C10 number of 51. It has clean burning characteristics. It's a substitute for DME and LPG and LNG. So DME is a very good fuel. DME is emerging as a LPG substitute even in the kitchen. So you can use both of them directly in the internal combustion engine. You can use dimethyl ether as a substitute for diesel. You can also substitute it for household kitchen fuel. You can use methanol in direct methanol fuel cells. Okay. And you can convert both of these into olefins. So theoretically, you can make gasoline and diesel from methanol and DME both. Whether that is cost economically viable or not, that is something that needs to be looked at. In India, it is in direct relevance of the government's ambition. 10% reduction in the oil and gas import by 2022 was promised, and they are going to play a very important role here. Prime Minister's Ujjwala Yojana, even in Prime Minister's Ujjwala Yojana, LPG can be substituted by DME. LPG is a very scarce fuel. We don't have too much of it. And apart from transportation, it can be used in telecom towers and railways, both these fuels. Similarly, this methanol can act as a drop-in fuel for SI engines. DME can be a drop-in fuel for CI engines. And burning of the methanol does not produce NOx, SOx, and particulate matter. So this is the entire landscape of methanol and DME. And methanol and DME both can be produced from coal, natural gas, biomass, municipal solid waste, and atmospheric carbon dioxide. This I have already informed you that the cost of the methanol production is going to be quite cheap. If we produce it on an industrial scale, I'll show you those numbers. The numbers are like 12 rupees to 15 rupees per liter is what is the cost of production. But then there are some limitations of methanol as well. And the first limitation is that it has lower heating value because of 50% presence of oxygen in it. And they produce more formaldehyde emissions during combustion because CH3OH and HCHO. HCHO is a natural combustion product. So there you can have formaldehyde emissions. And they are completely miscible with water. In case of any spill, there could be problems. It is slightly more corrosive than gasoline to copper, brass, aluminum, rubber, and many plastic parts. But then, this is easy to tackle. This is an engineering problem, and every engineering problem has an engineering solution. So that's not really a big deal. It can damage fuel lines, tanks, cascade, or metallic part. Again, this is something which is not unsurmountable. And due to low vapor pressure, alcohols have poor cold weather starting characteristics. Again, this problem is not something that cannot be solved. It can easily be solved. Now, this one picture I gave to actually summarize, and this one to explain, what this concept of methanol economy that the government is talking about is. So, here you see all kinds of biomass that you can think of: high ash coal, kitchen waste, agriculture waste, garbage of the society, city garbage. All this you take. This becomes a feedstock in your plant, and then you undertake you put all of that through the process of gasification. You gasify it, and once you gasify it, you produce carbon monoxide and hydrogen. And once you produce carbon monoxide and hydrogen and you correct the stoichiometry, that means for every carbon monoxide atom molecule, you have two hydrogen molecules available, then without any emissions, you can produce methanol. Okay. C, this is C, this is H3, this is O, and this is H, CH3OH. Now, from the methanol, as I said, DME is a close cousin. So what you do is you actually bring two methanol molecules together and remove water from in between. So that means this one CH3 group, this is another CH3 group. This is connected by one oxygen and H2O is taken out. So this methanol and DME are the fuels which can power your entire activities, such as, your ship industry, your agriculture industry, your transport sector, your industrial furnaces, your power plants, even the power plants can be powered by methanol and DME. Okay, so you can actually use the methanol as pure form. You can use methanol gasoline blend. You can use methanol diesel blend. You can use methanol hydrogen blend, methanol biodiesel blend, methanol DME blend, methanol LPG blends, methanol water blends, methanol gasoline ethanol blends, and so on. So you can do a lot of mixing, and I think a lot of researchers from India will test all this in their engines and produce one paper. Send me one paper on fuel for consideration in fuel, which I am not going to accept. So there is a lot of work that is going on in this space. Okay, so if you look at the methanol experience worldwide, I'll just share what is happening all over the world. Is it just Indian fantasy, or other people are also working? So let's first talk about China and look at this figure. This is from 2005 to 2014. And if you look at this is production in million tons. Okay, so million tons, that means 2014, about 40 million ton methanol was produced. How much is 40 million ton? In India, we consume roughly about 200 million ton petroleum products, and China produced 40 million ton. That means 20% of what India is consuming by methanol. And then, DME is about 5 million ton, and then this is CTL, is coal to liquid. Coal to liquid is basically hydrocarbons that are produced from coal. Okay, so there are a lot of reserves of coal exist. 12.8% of the coal reserve is there in China. And coal to methanol is playing a dominant role in methanol production in China. And then, they also have 5-year plans, and then they have produced a large number of vehicles. All these vehicles, that you see here, trucks, buses, cars, scooters, and motorcycles. They have 2 million vehicles which are running on methanol in their economy. And by the way, the methanol is not being promoted by government. Methanol is being promoted purely by economic reasons, because it is cheaper, it gives you good performance, and environmental benefits of lower pollution is a after effect, is a consequence. So I think in India also we have a similar situation. I don't care about the environment. I care about how much money I can save by switching to a new fuel. And if the new fuel also is beneficial for the environment, that's good. So this is what is driving in China. So most of the taxis in China now operate on methanol, because the fuel is cheaper and the maintenance is less and everything is good. So if you look at this Chinese map, different fuel blends, M15, M30, M85, M100. These are different provinces, Xinjiang, Jiangsu, Shandong, Hebei, Shaanxi, etc. So this shows different fuel blends being available commercially, not promoted by government. Okay, these are all promoted by private parties, and this whole methanol revolution in China is purely driven by economics. So why can't we do it in India? We can also do it in India. It will make a lot of economic sense to do it in India. Similarly, if you look at other methanol blending activities outside China, there's a lot of work going on in Russia and Australia, in Alaska, in United States, Trinidad, Tobago, Iceland, UK, Egypt, Iran, Turkmenistan, Uzbekistan. These are the places where this is being explored in at different levels. If you look at the experience of Sweden, in the Sweden, they have set up a plant which is called Warmlands Methanol AB. It actually converts wood biomass, 1,000 tons of wood biomass per year, per day, and it converts all this woody biomass that is generated in the farms, in the forest. It converts into methanol, and 4 lakh liters of methanol, biomethanol per day is produced for different applications. Similarly, I talked to you about the methanol from thin air in the Iceland. There is something called George Ola Renewable Methanol Plant, and this is world's largest CO2 to methanol plant. It uses the geothermal energy or hydrogen energy to split water and then the resultant hydrogen to produce methanol using atmospheric CO2. That means it absorbs the carbon dioxide from the thin air in the atmosphere, uses primary CO2 free energy to produce hydrogen, let this hydrogen react with the CO2 to produce methanol. And this has a capacity to produce 5 million liters of methanol per year, and it recycles 5.5 thousand tons of carbon dioxide each year. So this much CO2 is removed from the atmosphere, 5 million liters of methanol is produced every year. George Ola was a 2007 a Nobel laureate, University of Southern California. He's the guy who gave this concept of methanol economy, and this whole plant is named in his memory, in his remembrance, for his contributions to the concept of methanol economy. There is a city called Edmonton in Canada. Just 1 second, there is a phone call, I guess. हाँ विक्रम, मैं लेक्चर में हूँ. हाँ चले जाओ ना. So this city in Edmonton, this is a global game changer in methanol economy. So there is a company called Enerchem Alberta Biofuels. What they do is they take the garbage, they accept the garbage from the municipality. So municipality collects all the municipal solid waste, brings it to them, and gives them money as well. They give them the waste and they give them money and say that, okay, you dispose of this waste. So they dispose of the waste and they take the money from them. They convert that waste into methanol. So 4 lakh liters of biomethanol is produced by this plant. By selling this methanol also they make money. And by accepting the garbage from the city of Edmonton, also they collect money. So now the city of Edmonton, 90% of the garbage produced in the city is accepted by this plant and they make a lot of money out of it. It's a profitable venture. Why can't we have such a situation in our country where every municipality, every city collects the garbage and give it to some entity which, along with some money to dispose it, because disposal otherwise, is a big problem. If we don't dispose it off properly, this is what you have in our country. This is not a mountain. This is a mountain of garbage. This is outside Delhi, capital city of Delhi. And I think if you look at Delhi, at least on all sides, you will see such mountains. Every city, this is the situation more or less everywhere in India. These landfills are brimming to the seams, and in fact, they are just, on fire, perennial fire all the time. It puts so much of pollutants into the atmosphere. There is no space available for new municipal solid waste disposal. Why can't we convert them into methanol? This is a waste to wealth conversion in a very, very environmental friendly way. And a lot of environmental problems can be actually disposed of if we make right policies to take care of our garbage. Now, if you look at the policy of the government of India on making this methanol economy a reality, so India is basically looking at converting it high ash coal into methanol, and for this the technology is being developed by Thermex and IIT Delhi, and the route is going to be that there will be first R&D scale units which have been already successfully tested, and there will be pilot plans of 1 ton per day. Once this is successfully done and some lessons have been learned, then there will be a demo plant of 100 tons per day, which will be installed in a few locations, and based on the experience with 100 ton per day, there will be commercial plants of which will be using 1500 to 5000 tons per day methanol, and the target is that we should produce 60 million tons of methanol per year in near future, so that lot of oil import can be reduced and substituted by methanol economy. So the time scale is that 100 ton per day SPV mode, 6 units are to be planned. I don't have the current status whether it is on a plan or not. And then 1500 to 5000 ton per day plant will be open into 2023. And I think this Talcher, there is a big thermal power plant coming up there. A lot of methanol will be produced there. So there will be a lot of sites that have been identified for setting up these units. These are the 6 coal field units where 100 ton per day and 1500 to 5000 ton per day kind of units will be set up. Now coming to the cost, in India we have a very high ash content coal available, and much of this coal, even up to 50% ash is there, and that is not good for any commercial activity, including steel industry or thermal power plant. All such high ash coal can be very easily put to methanol conversion in a very cost economic manner. And so here, the cost of methanol production is shown. So the cost of methanol is shown here. The water cost is shown here. Electricity that is required is shown here. Catalyst and chemicals, manpower cost, spares, finance cost, everything put together. The cost of methanol production that is estimated is about 14 rupees 34 paisa per kilogram. That's about 12 rupees per liter is what is the cost. So 50% energy value, that means if you want 1 liter equivalent diesel petrol, you will require 2 liters of methanol. So that's about 28. 2 liters of methanol will be 24-25 rupees. If you add GST and profits, another 15 rupees you add. So 40 rupees you will have fuel available in the market, which will be having equal energy as that of gasoline or diesel. So that means per megajoule energy cost, if you take methanol route, will be 50 to 60% cheaper compared to gasoline and diesel. And that's going to transform the economy of this country if it is implemented in a proper manner. Second route is based on the municipal solid waste to methanol. And here, again, you have gasification, and from you have an existing plant of municipal solid waste. So it is modified to methanol, and then commercial plants of 40 ton per day, accepting about 140 ton per day of RDF or municipal solid waste. So they are being tried, and already in Washim in Maharashtra, one such plant is actively being looked at by Thermex. There are many processes. So coal to methanol conversion process has 2 parts. One is coal to gas production. So you have air and coal coming. There is a gasification unit. Then there is a shift gas, cleaning, etc. And once the clean gas available with a stoichiometry of 2, that means for every carbon monoxide, 2 hydrogen is available. Then you go into methanol synthesis and distillation unit, and finally you have methanol coming out. So this is the commercial plant layout. And this is not a rocket science, very simple catalyst, copper and zinc on alumina. They can be used, and there are many process licensors. For example, coal to syngas, the process licenses are available by so many companies from Shell, GE, CB&I, Lummus, Siemens, Lurgi, KBR, Mitsubishi. And then syngas to methanol also, Davy, Holder Tropsch, Lurgi, Linde, Casale. These are the companies which gave the process licenses for this. So basically by taking two process licenses, if you don't want to develop your own, you take two process licenses, you will be able to convert coal into methanol in a easy manner. I will not move into this. So let me just focus on the methanol in IC engines. Again, the octane number is very high, 106, 105. So higher compression ratio engines can be used. And we know that if we increase the compression ratio, the efficiency is also higher. So if you design the engines for methanol or methanol blends, they can have higher compression ratio and therefore they can be more efficient. I have also mentioned about higher latent heat of vaporization, which is going to cool down the charge, and therefore the boosting will be more, volumetric efficiency will be higher, and therefore the engines will be more powerful. You can produce more power out of the same per liter of the cylinder displacement. And due to higher autoignition temperature, these fuels are safer for transport and store. They have better fuel conversion efficiency than gasoline. And due to larger heat of vaporization and better resistance to knock, ethanol is best option for small turbocharged engine typically used in the cars and trucks. How to improve the combustion and emissions? For that, you will require a lot of research, very systematic research. And so first you have to look at the fuel injection equipment. You have to look at and this slide gives you a lot of ideas about what kind of research we should be doing in India. What is the need for research in India, in which areas? So one is that if you try to look at fuel injection equipment improvement, injection delays, injection durations, injection rate profiling, that is one area. You can look at, spray development, spray tip penetration, spray angle, Sauter mean diameter of the droplets, bulk air fuel ratio. All these things can be also looked at. And then you have to look at the combustion characterization. That means you have to look at the thermodynamic analysis, rate of heat release, bulk temperatures, performance of the engine, thermal efficiency, emissions, and so on. Fourth is you have to look at the emissions, soot, nanoparticle, NOx emissions, and how to control them. These four areas, if you do, you will be able to develop a hydrogen fuel, the methanol fueled engine without any problems. So in India, if we want to adopt methanol, the roadmap is going to be that we have to develop the engine, we have to do the combustion optimization, we have to look at the emission certification and emission development, after treatment system development so that they meet the Euro 6 norms. Then we have to do the component refinement and cost reduction. We have to make sure that, they are compatible, the materials are compatible with methanol. We have to demonstrate the reliability by long duration endurance test. Then we have to develop the fuel infrastructure. We have to look at fuel certification, fuel regulations, fuel practices, fuel distribution practices. And then we have to build up the infrastructure once the protocols have been established and put in place. And finally, the overall process refinement, reduction in the cost, increasing the efficiency, and so on. So this is the roadmap for methanol adoption in India. Now the hurdles of methanol in India is that there is complete lack of awareness in the public. People don't know what methanol economy really means. What are the prospects? What are the contours? What are the benefits? And unlike petroleum industry, there is no active lobbying group. There is nobody who says that we should go for it. There is no big money involved. High capital investment is required for production plant. And right now, the rich people in India have not realized its potential. And then the last, but the most important challenge that we have is from the fuel injection system. The fuel injection system, injectors, fuel pump, etc., 95% of that market is dominated by Bosch. And Bosch is reluctant in giving the warranties unless and until they develop methanol compatible fuel injection systems and they give warranties on it, the whole program cannot succeed. So this is very, very important when we look at compatible materials. Okay, so I have written this one article for Nature India, Pollution Woes, Is Methanol a Solution? This was published on 7th February 2018. It is free to download. You can just look at Nature India if you want to read it. And this is a very brief article which says, uh, what are the prospects and why we should look at it. So the methanol, the limitations, as I said, heating value, formaldehyde emissions, miscibility with water, corrosiveness, can damage the fuel lines, low vapor pressure. These are some of the challenges. So should we look at DME? DME, is another fuel which is very important, and this can be produced from natural gas, coal, biomass, again by syngas generation. So just like methanol, you generate syngas, and from syngas, either you do direct DME synthesis or you can go via methanol route. You produce methanol and then dehydrate methanol to produce DME. Both are options are open, but you can also do DME synthesis direct. And this DME can be used for power generation as LPG substitute and transport fuel. Okay, so DME has a lot of opportunities because conventional diesel engine with slightly modified fuel injection system can adopt to DME. This is one big advantage. It has large market potential. It has high CTN number of the order of 65 plus. It has very quiet combustion. If you run a diesel engine on DME, the noise will be very, very less. It has clean burning characteristics. It's completely sootless. I mean, however bad the engine may be, but you will not see particulate coming out. And it does not have any sulfur, so SOx reduction is 100%. It is extremely volatile, so mixing of the fuel and air is very good. It leads to smokeless combustion. And there is infrastructure, which is similar to LPG, can be used for the transportation. So LPG infrastructure is quite established in India. The same infrastructure can be used for distributing the DME in the country. The challenges include that there are regulatory hurdles. There is a LPG distribution network need to be slightly tweaked. Lubricity issues is a big problem. So additional, lubricity additives need to be added. Otherwise, the fuel injection pumps in the engines will have problem, and there will be lower viscosity. Government regulations need to be in place. Lower lubricity issues need to be handled. Storage and seal compatibility. Okay, I will just leave you with this. I'll just take a blue break for 1 minute. Please review this schematic.
Okay, sir.
Okay, so if you look at this, as I said, this is natural gas, coal, organic waste, or biomass. All this can be used to produce syngas. So if you produce syngas, then either you can have a methanol synthesis and then DME synthesis, or you can have direct DME synthesis. So this is one way of producing DME. The other way of DME synthesis could be that you use CO2 free primary energy such as wind, hydro, geothermal, solar, wave energy, tidal energy, or nuclear energy, and you produce electricity. Use that electricity to do splitting the water into hydrogen plus oxygen, and then use waste CO2 either from the power plants or from thin air. You generate CO2. This CO2 then reacts with this hydrogen to do methanol synthesis, and then this one-step process you can do DME synthesis, methanol dehydration process, and then you can generate DME. So is the DME production clear, how it is produced?
Yes, yes, sir.
Sir.
Okay, so DME production, you have these two molecules of methanol, you remove the water and you get DME. And this is high C10 number, 60, 65 compared to 48 to 51 for regular diesel. And this is DME is non-toxic, non-teratogenic, non-mutagenic, and non-carcinogenic. Very easy to produce, it's very easy to ship, it's very easy to dispense. It's a gaseous form at normal temperature and pressure, but if you compress it to about 5 bar at normal temperature, it becomes liquid. So just like LPG, is liquid at 5 bar, similarly DME is also liquid at 5 bar. And therefore, it's a good substitute for LNG and LPG. And this gives completely soot-less flames during the combustion. And these are some of the visuals of DME bus that is plying in Japan, DME truck which is plying in Denmark. There are many companies which are, Mack truck has a DME truck. And so the advantage of dimethyl ether over conventional diesel is that you have decreased emission of NOx, hydrocarbon and carbon monoxide, and its combustion does not produce any soot. If you look at this is the emission and the fuel consumption on the y-axis. And this is the brake specific fuel consumption. The red one is diesel baseline and the blue one is DME plus oxidation catalyst. So BSFC is low in DME. Hydrocarbons, you can see there is a huge difference in hydrocarbon emissions. There is huge difference in carbon monoxide emissions. And if you look at the particulates, there is no particulate. The axis is 0. That means this is one of the big advantage of DME. That DME does not produce any soot, 0. NOx also is quite low. So, you can see that compared to diesel, the DME is quite environment friendly and its pollution levels are very, very low. This just shows the well-to-wheel GHG emissions. This is well-to-wheel GHG emissions of different options, different types of vehicles, which are fitted with different technologies. I will not go into details of it, I'll skip it. So the challenges of using DME in the engines, first challenge is leakage. The viscosity of DME is very low compared to diesel. This is lower by a factor of about 20. So that means if you are using the same fuel pump and same fuel injectors which are used for diesel, from the clearance volumes, this will leak out very, very easily. So leakage of the DME from the fuel pumps and fuel injectors which are used for diesel is a big issue. And therefore, if you have to use the fuel pumps and fuel injectors, either you have to reduce the clearances or you have to develop dedicated fuel pumps and injectors for the DME, and they will have lower leakage issues. Second problem with lubrication, DME, as I said, does not have lubricating properties. Even in diesel, the lubricating properties are provided by sulfur compounds. And we all know that with increasing emission norms, Euro 2, Euro 3, Euro 4, we are continuously reducing the sulfur compounds. From 500 ppm to today, we have about 15 ppm sulfur. So what that does is, even for diesel, there are lubricating issues in the fuel pump and fuel injector. Okay, and we have to address them by adding lubricity additives into the fuel. These are called multifunctional additives, MFAs. So similarly, similar to MFAs that are added in diesel, we have to add some kind of DME additives in the DME as well. If we don't add, then what will happen is that the fuel pump and fuel injectors will prematurely fail. They will fail very frequently because there will be wear. If the lubricity is not proper, there will be wear of the component, and fuel pump fuel wear is very dangerous. It's very expensive to repair. So therefore, you have to add some kind of additives in DME. Without that, we should not even try to do any experiment on the engines. This is very important that we worry about lubricating issues. And then, third issue is storage. You need a storage tank which is almost twice the conventional tank, because you know the DME has lower energy density compared to diesel. Its density is also less, and it has higher oxygen content also. So if you want a similar type of tank of the range of the vehicle, then you will need double the size of the tank. So this is also one challenge of using. Okay, so this is now, so far we have covered the DME and methanol together. Now let us just look at them together. So DME versus methanol, you know, there is no conflict. There are different niche areas for these fuels. Methanol is good for SI engine, but it can also be used in CI engine, but with limited benefits. It has higher octane number of 106, but it has poor miscibility in diesel. More than 10%, you know, start separating. So to avoid the phase separation, you need to add different additives so that the methanol diesel blends do not separate or phase out. Then lower blends of gasohols. Gasohol means gasoline and alcohol. Can be used in older engines without any problem at all. So if you have an old car, you can immediately put methanol in it and you can start using it, no problem whatsoever. No separation problem. Separation problem only exists with diesel. If you have newer engines, you know, you can design the newer engine with higher compression ratio to use M85 or M100 to take full advantage of methanol, and you can have superior efficiency engines which are high compression ratio. And it's a solution for two-wheelers. It's a low-hanging fruit, and IIT Kanpur is working big time on developing two-wheelers. We have already developed two-wheelers for 100, 125 cc using M15. We have developed two-wheelers, 500 cc two-wheeler using M85 with ECU, etc. So all those things have been done in our place. And if you happen to come to IIT Kanpur, I'll be very happy to show you all those. Similarly, if you look at DME, you know, DME is a high C10 number fuel. It's used for diesel engines only. Methanol can be used in both in SI and CI, but DME can only be used in CI engines. And this is, since it has higher compression ratio, so a higher octane C10 number, so higher compression ratio engine should be developed. It gives you very low particulate matter, low HC, low carbon monoxide. NOx emissions are higher, but they can be reduced with EGR and after treatment. Very easy to comply with Euro 6 emission norms. It's a simpler and cheaper engine technology with maximum pressure only up to 500 to 600 bar. So if you have a CRDI vehicle, you want to convert to DME. In fact, if you want to make a new one, my guess will be that the vehicle will be cheaper by at least 2 lakh, if not more. So it's a solution for light duty and heavy duty vehicles, and this can be easily adopted. So to conclude my talk, you know, I would just like to say that for sustainable future, there is no single solution. We have to look at multitude of solutions. IC engines are here to stay. So if somebody says, you know, that battery electric vehicles are going to be there, you know, same, okay, thank you very much. We'll see after 2 years. I mean, I have been fighting this perception for 5 years now, and EVs are nowhere, and they will have some role to play, definitely, but they cannot be 100%. So you have to just take that line. They have to, but IC engines have to become cleaner, greener, meaner, and more efficient. So if you have to combat the electric vehicle threat, you know, we have to make them more efficient. And for next 30 to 40 years, there will be wide range of vehicle technologies and fuels in developing market and developed economies. For example, you know, in the fuel space right now, you know, it is only diesel and petrol, but other technologies such as gaseous fuels, HCCI, hybrid vehicles, fuel cell vehicles, all these will find its way into the vehicle technology that will be coming in the future. Finally, you know, if the engines have to survive, we have to make sure that we don't smell the exhaust, we don't see the smoke, we don't hear the noise from them, and that's the only way to survive. Thank you very much. This is my email ID. If you have any questions, you can let me know. Otherwise, now I'm open for discussion.
Uh, Thank you, sir. So we have some questions from participants.
Yeah.
One participant has asked, what is the effectiveness of biodiesel as an alternative fuel, considering effect on food crops?
Now, I told you that if it is produced from non-edible non-edible vegetable oil, I think that is one way we should look at. We should not be producing biodiesel from edible oils, because we are already importing 50% of the edible oil from overseas. So it doesn't make any sense to import the oil to eat and then divert the supply to make biodiesel. As far as the biodiesel is concerned, whether you make biodiesel from edible oil or non-edible oil, once biodiesel is made and once it meets the specifications, origin really does not matter. And that is one problem that I'm facing these days as the editor of Fuel, that, people like to churn out papers after papers from different vegetable oil, they convert to biodiesel, and then they think that this is novel. This is not novel. I mean, you change the oil, that doesn't make it novel. You change the oil once you make biodiesel, the chemical composition is almost similar if it meets the specification. And then, it becomes a similar routine work.
Okay, thank you, sir. Now, second question is from Professor Joseph Soni, sir. He has asked, sir, why we have still not opted methanol route, as it seems promising cost-wise as compared to gasoline and diesel.
Yeah, so methanol was realized about 5 years back. And methanol right now is not available commercially. So government has realized its potential, and Niti Aayog is throwing its weight behind it. So there are efforts in the government to actually produce methanol on a large scale. And there are different teams of experts working on different aspects. For example, IIT Kanpur was tasked to develop technologies for different applications. We are looking at use of methanol, different blends for two-wheelers, four-wheelers, gensets, DME. So we are working on the utilization side. Similarly, IIT Delhi was tasked with the task of developing the production technology with Thermex. So they are working with Thermex to develop the production technology. Similarly, IOC is working on distribution network. There are some teams working on making the rules and regulations and BIS specifications. There are some teams which are working on notifying the methanol as fuel. So once a fuel has to be brought commercially, there is a lot of the lot of work that is required, lot of background work that is required. So there are about 200-300 experts, if not more, are working, and this is probably the first time in the history of independent India that some fuel is taken so seriously by the government. And there are systematic efforts. I don't know whether it will come or not, because commercial success of any fuel is very different from the technical success. And as a researcher, we can only ensure technical success of a fuel. Commercial success is altogether different ball game, and it depends on a lot of policies of government and a lot of other factors which are beyond our control as scientists. So we are working, we are doing our role. Let us hope that it becomes a commercial success as well.
Yes, sir. Thank you. And Dr. Rakesh D. Patel has asked, sir, how many percentage use of methanol as blend in petrol?
So as I said, petrol engine I can run on 100%, but I don't want to, and I have a difference of opinion with a lot of other experts who promote 100% use because of the problem of safety. If I take a bowl filled with gasoline and I put it on fire, I can see flames coming out very clearly. But if I put a bowl full of methanol and if I put it on fire, I will not see any flames. So, and there will be fire, there will be flames, but I just cannot see any flame because there is no shooting happening there. Okay, soot is what glows and gives incandescence to the flames. So M100 fuels are completely invisible, and that makes it inherently unsafe to use. And therefore, I mean, even at the highest level, I have put my point that, okay, if you give it to me in writing, I will use, but I will also give you it in writing that M100 is risky, and if there is a problem, I will not be responsible for it. So I advocate up to M85. That means put 15% by volume gasoline purely because of safety reasons. Because then you can see the flames, you can see some flames. And in case of any accidental spill or accidental fire, you will have safety. You will ensure the safety of the rider. You will have you will ensure safety of the people. You will know what is the extent of fire. Once you can't see, you know, what are you going to extinguish, right? So it becomes very, very unsafe. And so in my lab, we are working on a carbureted engine, which is using 15%, because for that I don't need to make much changes in the engine technology. In fact, uh, we have our technology for M15 is costs about 50 rupees. If you have an existing vehicle, only 50 to 100 rupees is what it will cost to make it compatible with M15. But if it is M85, maybe few thousand rupees will be required for something like a bullet motorcycle. But if it is done commercially by the company itself, it is not, in both cases, no expenditure will be required. I mean, it will cost the same. So the vehicle cost, if it is done commercially, will be same. If it is retrofitted in the old vehicle, then there will be some cost, 100 rupees, 50 to 100 rupees for M15, and maybe about few thousand rupees for M85. I hope I answered the question.
Yes, yes, sir. Thank you, sir. And the last question is, Professor Ronak Shah has asked that when we add methanol in fuel, what major changes are there in the IC engine injection system?
Yeah, that's an important question. Uh, See, ultimately, you have to look at what kind of injection system you are using. For example, I told you, I'll just take the example of these two-wheelers. So if you are doing a carburetor two-wheeler, right? The carburetor two-wheeler, the changes that will be required will be only in the jets. Because you see, once you use M15, now this 15% part will have lower calorific value, 50% calorific value. That means the fuel that you will be using will be having 92.5% calorific value compared to gasoline. That means for the same speed, for same power, you will have to increase the fuel flow rate by about 7 to 10%. And for that, you need to increase the jet size. So carb calculations need to be done, and then the jet size need to be increased to get the same power output, same torque characteristics from an existing engine. So this is one change which you need to do. Second thing is that, you know, the methanol, once you put methanol, it is not compatible with rubber and polymer because it attacks the rubber and polymer. So all the seals, O-rings, etc. need to be actually changed. And all the material which is attacked by methanol also need to be changed. So you have to make sure you know what kind of material is being used. Some material compatibility studies need to be done. So this is as far as the carburetor engine is concerned. Second aspect is the fuel injection equipment for PFI engine, more multi-point port fuel injection. There it is more complicated because there you have to actually worry about the ECU calibration. All the EFI engines have an ECU. So you have to actually do combustion optimization at different speeds, different load, different kind of optimization need to be applied, different kind of compensations need to be given. So all those things need to be taken care of, and that's a little bit involved development process in which there are a lot of changes required in the fuel injection system. So structure per se remains same, but the software changes. In the hardware, you basically look at the compatibility of methanol with your existing material. Okay?
Yes, sir. Thank you very much, sir. I think we have asked all the questions that we have received from different participants.
One
Dr.
moment, Hira.
Yes,
One
yes,
moment.
sir.
Sir, my friend Anurag Emmanuel has asked me to thank you personally to have accepted our invitation and has sent his regards to you, sir.
Okay, thank you.
Sir, one more thing. You said Chinese people are working on liquid sunshine green methanol for mass deployment around 2070. Sir, is there any similar research work going on in any of the IITs or anywhere in India?
This is Chinese government plan. IITs are not government. IITs have very small footprint. The government
Okay.
has a plan and then accordingly decide.
Okay. Thank you, sir.
So,
The government makes such plan. We need that in India at national level.
yes, yes, sir. So, the sir has nicely explained all the aspects of future fuel or fuel for sustainable future. So thank you very much, sir. Sir, you have given us the need, use, and benefits of methanol fuels and DME fuels. Also, you have shown us the research that are being conducted at different locations in the world, and what are their current situations in concurrent time, that you have also explained to us. And you have also shown the roadmap of methanol for India specifically. So we are very happy that you have shown very exhaustive data on your research. So it will be not an exaggeration if I say that you are one of the energy scientists, and we are lucky enough to interact with such a great personality. So on behalf of STTP team and all participants, sir, I convey you the very much thankful to you, and thank you very much for delivering your session, sir. Thank you very much. We have enjoyed your session a lot, sir.
Thank you. Bye-bye.
Now, there is a time of lunch break, so I will request all participants to please get your lunch and be ready at 2:45 p.m. We'll start our next session at 2:45 p.m.